Okay. Well, this is an analysis of survey microdata on biomarkers linked to satellite data, daily data on weather conditions in Costa Rica. And the research questions were if there are seasonal variations in biomarkers in this tropical country, and if these variations are related to the weather. And this is a relevant topic for research and medical practice, and also to assess the consequences, the potential consequences of climate change. As a background, seasonality is a well-documented issue for many biomarkers, but mostly in places distant from the equator. And this usually is related to extreme variations in temperature and sunlight. In the tropics, weather variation is different. For instance, this variation is small, usually in temperature, and could be very high in rainfall or other conditions. And there is no such a thing as cold weather. And the study was conducted in Costa Rica. You can see this tiny country, 10 degrees north of latitude, with two seasons, a dry season from January to April, and a rainy season from May to December. It's cooler in the Central Highlands, where 2/3 of the population lives. The maximum daily temperature has a mean of 70 Fahrenheit over the year, with a small standard deviation of less than 10% of this mean. And the rainfall has a mean of 7 millimeter a day, which is a lot, and with a very high variation of almost 100% standard deviation of the mean. The meteorological data are daily estimates from a NASA website that we interpolated to the exact participation location, which was possible because we have the household coordinates we took during field work with a GPS device. And we will work just with the average of 30 days previous to the interview. And the data are for 13 biomarkers from a national sample of 2,400 adults aged 60 years or more. All participants have two measurements, almost 2 years apart, and we have measures for more than 4 years of continuous data collection. Most biomarkers come from venous blood, we drew in the households, and these include the usual lipids indicators, and creatinine, the DHAS hormone, telomere length, and the C-reactive protein inflammation indicator. In addition, we also include in the analysis blood pressure, body weight, and abdominal circumference. All the variables were normalized to a mean of 0 and standard deviation of 1 for comparability purposes. And we estimate the different effects with panel regressions on individuals and using only fixed effects models. That means that we are focused on the within individual variation rather than the between individual variation. The dependent variable is each biomarker, and as is customary, we use a sinusoid transformation of time to force the cyclic character of seasonality. Okay, let's go to the results. In this radar plot, with weeks of the year running clockwise, we show two extreme examples of seasonality. Body weight with almost no seasonality. The fit curve is almost the same as the zero means. And total cholesterol, which show an extreme seasonality with a peak in the middle of July and a bottom toward the first week of December. The difference between the peak and the bottom is the amplitude of the seasonal effect. And in the case of total cholesterol, this amplitude is 0.8 standard deviations. Okay, and this is a representation of the peaks and the bottoms for the 13 biomarkers. Okay, with a confidence interval. The great majority of points here are significantly different from the zero mean. And total cholesterol outstands with the highest peak by large in July and the lowest bottom in December. And for some reason, there is a concentration of peaks in July and August for many biomarkers, which is the middle of the rainy season. Although there are two interesting outliers, the indicator of diabetes, glycated hemoglobin, and telomere length, which peaks occur toward the end of the year. And for the bottoms, there are two clusters. The first cluster is in April, the warmest month in Costa Rica, and the other cluster occur toward the end of the year. Oops. Sorry. Here we go. And this figure shows the rain and temperature effects on biomarkers. Remember that the effects are measured in standard deviation. And this is the effect of a change in one standard deviation in rainfall or temperature. Biomarkers are sorted by the temperature effect. Temperature effects are evidently much larger than rainfall effects, which was kind of surprising given that the temperature don't vary that much in Costa Rica. And warmer weather increases significantly total cholesterol, creatinine, and triglycerides, and decreases significantly blood pressure, systolic and diastolic, the diabetes biomarker, and telomere length. This is a big effect. And rainy weather show significant and meaningful effects only on HDL, cholesterol, and telomere length. Rainy weather tend to increase the length of telomeres and the good cholesterol. And finally, this figure shows the importance of seasonality in the different biomarkers. The biomarkers are ordered by the total seasonality effect. And we present here also a net effect after controlling the rain and temperature effects. And this is measured by the red bars. And the difference between the blue and red bar is the fraction of seasonality explained by the weather condition. So an important fraction of seasonality is explained by weather in almost all biomarkers, especially in some biomarkers where more than 50% of the seasonal effect is reduced after the control for well condition. And this is for HDL cholesterol, creatinine, fasting blood glucose, and abdominal circumference. For telomere length and triglycerides, there is no reduction of the seasonal effect after controlling for weather conditions. So, conclusions. The data show the meaningful seasonal variation in most biomarkers. In part, this was driven by weather conditions, particularly temperature, which is surprising given the small temperature variation typical of the tropics. The results are robust, given that come from longitudinal data and fixed effect models. And these results are some warning for research and clinical practice, given that seasonal variations may confound comparisons of biomarkers taken in different dates. And the expected global warming of 3 Fahrenheit degrees for the next 25 years could, if our results are true causal effects, could increase by 10 to 13% the mean total cholesterol, serum creatinine, and triglycerides, and could reduce the mean telomere length by 10%. Well, that's it. Thank you.